very nice to meet with David. This is the first time, however, this is the world of the research. It doesn't have any boundary, and then it doesn't have any introductions through the email, meeting at the first time. It's like that we have been with him since long. I'm very, very, very thankful to meet you. And then I'm very, very thankful to meet with engineering people, because it is a interdisciplinary area where we need a lot of knowledge from the engineering aspect, and that is not able to build up with only with the knowledge from the physics. I'm very, very happy to join in this meeting. So, yes, I have seen in the schedules of this workshop, a lot of people have already talked about the physics and the algorithms and the prospect of the photoacoustic imaging systems. Now, I will more focusing in the instrumentation part, design and development, and the processing and all these things. And then to come in that way, I would need to browse back the very physics of the phenomena. That is what. Basically, though there is a part 1 and part 2, I am a bit sorry, I am not very much adapted to make the arrangement for the time bound and all these things. So I club it all together, and then if you have any, then please let me break it up. So I may continue. If the time permit don't permit, then I will stop it. So, so in the part 1, I will more focus in the microscopy. In the part 2, I will try to focus on the tomography from the design and development. So to start with, I would like to say the medical imaging has been advancing at very fast rate, and at a very, very unexpected rate, I would like to say, since the last half century, by the 1960s. Since its first discovery of the X-rays in the 1980s. So now everybody knows and accepts that medical imaging gives a significant contributions to the healthcare, in the sense that it improves the healthcare domains, from the diagnosis to therapeutic treatments to the healthy living and healthcare and all these things. So in this way, the journey of the medical imaging starts. Yeah. So from the invention of the X-rays in the 1880s, it was first do the imaging in his wife's hand. So from this point, it has been exploited for the clinical applications. Since then, it has been evolving to the introductions of the ultrasound imaging in 1920s, 1930s, and then the computed tomography, positron emission tomography, and MRI, all these things in the 1960s and 1970s. Since then, it has been evolving. All this imaging system has positive advantages as well as a negative point of view. Just to say that X-ray imaging, it gives the 2D images. Not only the 2D images, it is the dimension wrapping of the 3D to the 2D. So the 3D distributions is mapping towards the 2D informations, and this ultrasound imaging, it gives the 3D imaging. However, the image resolution is very poor, and the kind of the physiological information that we can get it from the ultrasound imaging is very limited, because it is fundamentally based on the imaging of the contrast distributions in the acoustic impedance that is given by the rho C. Rho is the mass density in the C is the speed of sound. From this kind of things, the kind of the physical information that we can derive is very limited. So more particularly, ultrasound imaging gives over only the structural information of the tissues. And then CT, that is the 3D versions of this X-ray, where the computed tomography is employed to get the reconstruction of the 3D images. So and then positron emission tomography and an MRI, all these things are giving a very reasonably good imaging resolution. However, it is very expensive to be done for the routine scanning and all these things. Since then, people has been looking for the introductions of the new imaging systems to address the kind of the limitations in the existing imaging modality for the clinical applications. So by the late 1990s, a new imaging modality that we call as the photoacoustic imaging come into pictures. Though it was introduced in the mid of the 1990s, it was only in the mid of the 2000s, by say 2005 to 2009, it is widely studied across the world. This is about it. This is about which I am talking about the design and development of the photoacoustic images. So, in this talk, I will, before going in depth to the technology of the imaging modalities, I would like to come up with the potential and probability aspect of the photoacoustic imaging, and then I would like to give the details of the theoretical basis of the photoacoustic imaging that comprise of the two stages that I would like to say: generation of the photoacoustic signal and the propagation of the photoacoustic signal, and the instrumentations for the detections and the collection of the signal, and both for the microscopy and tomography, and the reconstruction regions for the microscopy as well as the tomography. And then from the detected signal, what are the physical parameters that one can derive of, or what is the design to extract that kind of the physical information from the detected signal that I would like to come up. So, photoacoustic imaging is rapidly emerging since the last 1 decade that I would like to say. So these are the marks where I found it, the research labs are doing the research over the globe. When I see, I think not less than 100 research labs are found all around the globe. Unfortunately, in India, not other than the numerical approach is not yet reported in the literature. So Li Hongwang, at the time of the Washington University, now he shifted to the Caltech, and Huawei Zhang, University of Florida, Paul Bergen, the UCL, Still Bergen in this month, University of Trinity, they are very pioneer in the development of the photoacoustic imaging system. Now it is very widely studied, so that it's not easy to say who is leading in this research area that I would like to say. So till now, I found it 2,721 literatures reported. According to the PubFact, that I found it 2 days back, against that 1,500 in 2015. When I check the rate of the publications, now it is 2.3 or so per day. 2.3 literature per day. This is how it is going on. And then very recently, by 2014, right? 2014, photoacoustic journal is established, dedicated for the photoacoustic images. Not only for the biomedical applications, people has already done for the industry and agriculture applications. It is nice to share you the story of the photoacoustic imaging. Just after the introductions of the photoacoustic effect, people have already studied for the basic science application, for physics, mostly for chemistry. It was only in the late 1970s people start for the biomedical applications. However, the imaging modality, it was come into pictures in the literature by the mid of the 1990s only, for the imaging, not for the signal analysis. Okay? For the imaging, for the clinical application, it was come in the mid of the 1990s. This widely studied and rapidly growing of the research area around the globe It is only because of the fact of the potential and the promising features that photoacoustic imaging have it. Firstly, it gives a high contrast and image resolution at the depth, not achievable with the highly dissolving microscopic modalities, just like the confocal, OCT, electron, or even a microscopy. People know these are the gold standards of the microscopy imaging that give a very high resolutions of the order of the nanometers and Armstrong. However, the limitation is that it is for the superficial imaging. It cannot be done for the thick sample, and not only this limitation, the very one more serious limitation that is not feasible for clinical application is that the sample has to be cut into slices and then it has to be introduced into the system. So because of this one, it is very completely destructive that clinical application doesn't like it. So in this way, I am just giving you the blocks. So every imaging modality has an inherent trade-off with the achievable imaging depth and the resolutions. In a sense, optical imaging technology, it gives a very high resolution. However, the penetration depth is limited to the few micrometers for the superficial imaging. On the other hand, ultrasound imaging, it gives a very high penetrations of the order of centimeters. However, the resolution is very poor, not suitable for microscopy imaging. So, photoacoustic imaging, it is a hybrid imaging technology that combines the advantageous features of the high contrast of the optical imaging technology and penetration depth of the ultrasound. Next, the potential features for the photoacoustic imaging is the high scalability of the image that we can achieve. Just to say that, including from the whole body imaging to the single cell, that can achieve up to the 500 nanometers. From the entire range of the nanoscale to the this one whole body imaging. Just to remind you, this is not a single imaging modality. For the photoacoustic, we have two parts. One is the microscopy and one is the tomography. However, that is very, very promising and challenging. So this is with the microscopy and this is with the tomography. In a sense that microscopy cannot get this kind of image, and then this kind of image cannot get this kind of images. However, the research in this domain are looking for the extension of the boundary of this microscopy to the higher penetration depth. In a similar way, this tomography that can achieve the higher penetration depth to achieve to the higher resolution. This is the kind of one of the challenging problem people are looking into it. And from the structural imaging at the multiple zooming scale. So this is zooming at a multiple scale by a single imaging unit. Though that is very simple for the optical microscope by changing the this one objective length, for the microscopy it is not so straightforward. So next, but another very important features of the photoacoustic imaging is that it gives the pathophysiological information of the tissues, in a sense that it can provide the this one physiological information that is related with the pathological state of the tissues through the measurements of the functional parameters, just like that hemoglobin, oxygenated hemoglobin, total hemoglobin kind of things that control the activities of the biological activities, just like the metabolism, molecular genetic activities, and the hemodynamics flow of the blood. And it has been exploited for the neurovascular coupling, the activities of the brain. Another aspect is the possibility of the development of the multi-imaging modality, combinations of the two or more imaging modalities together, so that the kind of information that we can get in from the one imaging modality to with the others. So It is very straightforward to get it from the photoacoustic because it is combinations of the optical and ultrasound that if the time permits, I can talk about this one, how we can build out without any problem with the multi-imaging modality with the photoacoustic. So ultrasound imaging that will provide the structural and the anatomical information of the tissues, and the photoacoustic will provide the functional and physiological information of the tissues. Lastly, so the imaging modality is non-hazardous and it is safe to help. So because it doesn't use the ionization radiations, and then it is non-destructive, that we don't need to cut the tissues, and then it is non-invasive. We don't need to introduce any kind of the drugs for improving the signal contrast. I would like to put a remark from the Professor Wabejang in his speech in the photonics. So photoacoustic imaging is an alternative to the conventional imaging of the MRI, CT, and all these things. That is what that I do believe in the near future. Till now, the application has been already exploited for the biological applications that I have shown you about the single cell imaging and oncology, ophthalmology, dermatology, epilepsy, brain imaging, and cancers. From the prospect point of view, very recently, since 2012, the clinical device has been brought for commercial use, both for the research applications, clinical applications, and laboratory use. These are the company that I found it. So Indra Lab Science for this kind of applications, and Visual Sonic for the dual imaging of the ultrasound and photoacoustic, and then IISER. This is a German base and this is a Netherlands base. That this one I'm not sure. I think very recently one Chinese company also come up that is for the low budget imaging systems. That is in the market. Okay. So with these brief introductions about the potential features of the photoacoustic imaging that will drive the motivations, I would like to come briefly about the theoretical models of the photoacoustic imaging. So in principle, photoacoustic imaging is based on completely based on the photoacoustic effect propounded by the Alexander Graham Bell in 1880s, which says that there is a generation of the sound wave due to the absorption of the light at a very short duration in a sample material which has an absorption and elastic. So in a sense that if the pulse of the light of the order of the nanoseconds is illuminating over the sample material, I don't want to say the tissue, I'm just saying the sample material that has a certain absorption coefficients of the optical. Then the light is absorbed by the materials because of the absorption of the light at the very short durations and the repeat heating. So it induces the thermoelastic expansion that I am explaining in a better way in the coming slide. And then because of the thermoelastic expansion, it will give the initial pressure rise. That initial pressure rise is given by these equations. So the details of the derivations that I am coming up. So initial pressure rise at a point is given by the optical absorption coefficients, and this is the optical points, the optical energy per unit area, and thermoelastic thermal coefficient of expansion, and the velocity of the sound, and the specific heat capacity and contact pressures. So this is the initial pressure rise. What it says that? So from the experimental measurement of this photoacoustic signal, then one can derive whatever the parameter that is involved in the right hand side. This is how the physics plays a role. That from this signal, what are the parameters that we can derive? How to characterize the photoacoustic signal? So to the base of knowledge, people start the exploitations of the extraction of the absorption coefficient from this one, because among these parameters, with a given phi optical energy, the main parameter that contributed The main parameter that contributes to the photoacoustic signal is the mu wave. The other are the parameters that give less than this one. Okay, it is not so easy because the signal strength is very low. However, people try to extract whatever the physical information from this one. So people already exploited for the velocity of the sound in the tissue, and people started for the extraction of the mechanical properties of the tissues. From all of this one, we can conclude with the different physiological informations. So, the entire physical phenomenon of the generations of the acoustic wave upon the irradiations of the light absorbing material for a short durations of the light can be described as a thermodynamic system that is characterized by the temperature, pressures, and volumes, while considering that the number of the constituent particles are constant, saying that no chemical activities are happening with the illumination during this process. That is completely validated. So, in this way, for the thermodynamic systems under our hand, that is the systems of the tissue material that is bounded by the imaginary boundary that is illuminated by the light. So, in a sample material where it reaches with the light illumination, that we can consider as a thermodynamic system, and beyond that one we can consider as a thermodynamic surrounding. So, if that is the case, we can characterize the phenomena by considering a set of the thermodynamic macrostat, that is the pressure, volume, and temperatures, as the independent variables. Considering that volume as a dependent on the pressure and temperatures, then one can extract these equations from these thermodynamic equation of states. This is completely from the thermodynamic. That I would like to say, for our physical system, we can very successfully explain from these equations, because in our tissue system, the number of the particle remains same. That is supposed to be. Otherwise, then it would be hazardous to the health. We cannot give any kind of the chemical activities, chemical process. Number of particles cannot be changed. So, if that is the case, from the thermodynamics, it has to be completely explained by the PVT. From this equation of state, then it would be characterized by this equation. If that is the case, by taking the differential, it is the case. So, from this one, by taking the relative change in the volume, then one can express to this one, where beta and k is given by this one, completely from the thermodynamics. In the sense that the rate of change of the volume is characterized by the thermal coefficient of the expansions and adiabatic compressibility. So, for the tissue material that is incompressible, while incompressible, it says that the volume cannot be changed. Just like the water, if we press it, the entire volume cannot be changed. Surface area will be changed. Just like this for the soft tissue, the whole volume is not changed. Simply, we can consider that the relative change of the volume, the change in volume with the thermodynamic process with respect to the entire volume, it is negligible as compared with the other term on the right hand side, beta delta T plus K delta P. So, in this way, for the short durations, then one can arrive with the equations of the heating equation, dQ equal to mst. Then by using this one arrives to these equations. This is what that I have shown you in the last time, in the previous slide. So by the measurement of from the experimental measurement of the P naught, one can extract the physical parameters on the right hand side. This is about the generations of the acoustic wave. So, photoacoustic imaging, I would like to break up into two stages. One is the generations of the acoustic wave, and another stage is the propagation of the wave. So, after the generation of this one, I would like to discuss about the generations and propagations of the acoustic wave. Yeah, let me tell you about this one. If we are talking about the distributions, then I would like to represent this equation in terms of this one that is dependent on the space, time, and temperatures. So, for the propagations, the physical phenomenon of the generations of the acoustic wave or the initial pressure rise that is due to the absorption of the light by the tissue material for a short duration, then it increases the internal energy and then it will increase the pressures because the volume is constant, so that locally the pressures is increased. Because of these localized variations of the pressures, it gives rise to the this one pressure gradient force that will drive the material to move from the higher pressure level to the lower pressure level. So this is the equations that governs the first order differential equation that governs the flow of the momentum due to the pressure gradient force. Because of the pressure gradient force, it tends to induce the movement of the particles. That particle is controlled by the conservation of the mass or the equation of the continuity. This initial pressure rise, it will give the thermoelastic expansion. This expansion has to be propagated through the medium that has to be controlled by the thermoelastic equations. So, I mean to say the whole of the three first order differential equations will governs the generations of the sound wave as well as the propagation of the wave. So, in terms of the first differential equations, these are the three equations. If we solve this equation, then one should be able to derive with the distribution of the pressure right at any point of time, at any point in the space in the tissue samples. That is our ultimate aim. So, however, it is not so feasible to solve all these independent three equations. Instead of this one, people used to do with the clubbing of all these three equations and then to arrive to the second order differential equations. This one with the initial condition of this one, that is the initial pressure rise and the rate of change of the pressure with respect to time during that time period is 0. So, with these conditions, one can arrive to the derivations of the second order differential equations. So, this differential equation is the time, and this is the time, and then with the assumption that this mass distribution over the tissue sample is same. With this one, we can simplify our equation. In the frequency domain, then one can arrive to this one. So the right hand side is a initial value problems. This is acting as a source term, and this is the simply the second order differential equations that governs the propagation of the wave in a medium. So, by solving these differential equations, one can achieve the distribution of the pressures at any point of time and at any point in the domain of our interest in the tissues. So, this is all about the development of the theoretical models for the photoacoustic imaging, both for the microscopy and the tomography. Okay. So, for the microscopy, I would like to say it is just a picking up of the signal at the source, that P0. For the tomography, it is the detection of the sound, that is propagation through the sample and detected on the surface. That is the difference. That I would like to discuss when I am dealing with the design and developments. So, photoacoustic imaging, generally it is of the two types. One is the tomography, one is the microscopy. That is what I am talking about. So this is the illumination of the sample with the pulse light. The initial pressure rise, it is picked up by using a focusing ultrasound transducer from the focal regions, such that this ultrasound transducer will pick up the initial pressure rise, that P naught, not the P. P naught it will pick up. So this is the microscopy system development. I will discuss later. And in the tomography, what is happening is that the transducer will be kept around the boundary of the sample. It will detect the sound wave, such that it is not detecting the initial pressure rise. It is detecting the sound wave that is propagated through the sample, and while ejecting through the surface, it is detected. That is consequence of the P naught, not P naught. This is the difference. So the kind of the reconstruction algorithm for the microscopy is not rigorous. However, for the tomography is rigorous. That involves the solutions of these differential equations. So in this way, the imaging modality that has the illumination part and the detection part. Illumination is completely sham. Detections are different. Detection as well as the reconstruction are different in these two modalities. So I would like to bring up you the state of the art in the design and development of the photoacoustic microscopy. So in this microscopy we have two categories. One is the acoustic resolution microscopy, one is the optical resolution microscopy. In the acoustic resolution microscopy, expanded beam of light is illuminating the surface. A tightly focusing ultrasound transducer is picking up the P naught. Need not be the light to be focused at a point, such that the lateral resolutions of the imaging system, it is characterized by the focal spot size of the transducer. Now, the kind of the resolutions that we can achieve with the acoustic resolution is very limited. Due to the literatures that I found is 60 micrometers, that is limited. Then people think of how we can achieve with a higher resolution. Then instead of this one, what about if we are focusing the light for illumination, then such that the focal spot size of the light is smaller than the focal spot size of the transducer. Then lateral resolution, the resolution along this direction would be characterized by the intersection of the focal spot size of the transducer and the light, so that as this is smaller, then it can be characterized. One more interesting is that the kind of the tightness of the focusing of the light and the ultrasound, the light can achieve far better. So in this way, with the OR form 1, now in literatures we can achieve up to the 0.5 micrometers, 500 nanometers. That gives the possibility of the single cell imaging. Okay. However, with this imaging modality, there is a limitations of the penetration depth. For the optical imaging, the scattering is very high. So for this kind, we need to tight focusing. If we need to tight focusing, it should be within the region of the rectilinear propagation of light. It should be within the diffusion of the light, before the diffusion. Then for the tissues, the diffusion happens of the order of the 1 mm. So the penetration depth is limited to the 1 mm. However, for this kind of the acoustic resolutions, the scattering of the ultrasound wave is very low. I think 1000 times lower than this one because of the wavelength. So it can achieve to the 4 to 5 mm. Imaging depth is very high. So this is all about. I was talking about the resolution is very high, and then here is a trade-off with this one. So very recently people also exploited for the endoscopy applications for photoacoustic. So people used to divide into 3 parts. So in this way, here is a difference in the optical illuminations. Detection is same, reconstruction is same. So when I am talking about reconstructions and design and development of the microscopy, I will discuss with the air pump where I did it. However, I would like to say it's same. Only the method is that how to focus the light, synchronize it together with this ultrasound and the dashboard. That is the difference. So to give an overview of the performance of the imaging technology, so all the actual resolution is same for air pump, then for the computed tomography, then this one imaging depth is very high. In the meantime, the resolution is very poor. Then the resolution is very high, penetration is very poor. All these things. So air pump is in the middle of some things. That is why people are also very interested for the brain imaging that we can use it. So I would like to come now with the design and development of photoacoustic microscopy that I would like to say that is for the acoustic resolutions. So the pulse laser from a laser source is collected as a beam, narrow beam, collimated beam, and it is split into 2 or more number, and it is coupled through an optical fiber. And then this optical fiber output is illuminating the sample surface. Instead of this one, we could have that to be the only one. However, by increase of the number, then the illumination can be achieved uniformly. That is the idea, at the cost of the loss of the energy over here and the complexity of the instrumentations. Okay, so this is the illuminations. Because of these illuminations with the transient irradiations of the light to the sample, it induces the initial pressure rise. This initial pressure rise, it is picked up by a tightly focusing ultrasound transducers, such that it will detect and capture the signal from the focal spot regions. Okay, this collected signal is pre-amplified because the strength of the signal that we achieve is around of the order of the microvolts. So that is not enough to process it, so amplify it, and then it is acquired to the data acquisition card. I used to include over here, data acquisition card over here, that is fitted to the system. So in this way, the photoacoustic signal that is detected and collected at a given position of the transducers from the tightly focused region in such a way that A-scan data is achieved by collection and transfer of the photoacoustic signal over the very narrow regions of the photoacoustic signal that can be achieved by the data acquisition system of the very highly resolving sample rates. We use around say 200 megahertz. So in a sense that at a one scanning position we get 1D data. If we move this one along a direction, then we will get a 2D data. If we scan in the 2D, then it will achieve the 3D data. So what I'm trying to say is that at a one scanning positions, then focusing over these regions, we discretize by the help of the data acquisition system. Then in the sense that at a one scanning position, we have the 1D data. If we move it, then we did the 2D data. If we move around, so we acquire the 3D data. Here is the one confusion. Scanning in the 2D will give the 3D data. So this is about the requirement. The one thing is that this movement is of the order of the micrometers that we cannot do manually. It has a number of steps, so it has to be controlled by the stepper motor. However, these excitations and the acquisition has to be synchronized. because the lifetime of the photoacoustic signal is of the order of the microsecond. It's of the order of microsecond, 10 to 15 microsecond. However, this equation has to be done before the excitation of the next pulse. So, for this laser pulse, this is a pulse of the width of the 5 to 10 nanosecond people used to do, or 1 to 10 nanosecond typically people used to do, and at the rate of the 10 hertz, we are using around 100 to 200 hertz. So within this range, we have to capture it. Then we have to capture and finish the capturing before the next pulse excitations. So this kind of synchronization is required. That is done by, in our case, that we use the lab view to synchronize all these things: excitations, movement, and acquisition and transferring of the data. Yeah, this is about quiz. I was talking about this is the focal spot size, and then we are taking the signal, and then we are neglecting all these things. So typically we are using around say 80 to 100 milliwatts, and then we use the 17 to 20 nanometers sampling rate. This one amplifier we use around the 39 dB, and then operating frequency of the ultrasound, we were using 1 to 100 megahertz, and beam waves of the 61 micrometers that we can achieve, so that the lateral resolutions is limited to the 61 micrometers, and the pulse wide and the pulse repetition frequency of the 200 hertz, and amount of energy that we are using is the 80 to 200 millijoule per second, centimeter square. So in our systems now we can achieve to the 100 hertz pulse repetition period, so that we can achieve the frame rate, higher frame rate of the imaging. This is the photograph of the whole imaging systems that is taken while carrying out the experiments in the small animals. So basically, this is from my postdoc in the University of Florida. So sample preparations, then acquisition system. So this is for the sample, the kind of the photoacoustic signal of this type. Okay, and this one we know I do the scaling for the back and forth. One is for the one direction, and another one is for the other direction. So this is the laser, and this is the oscilloscope. This is the amplifier. This is the motion control stepper motor, then this is a sample. I think that these are the optical systems that we do it. Yes. So for your briefness, I am just playing you the video that we took it during the experiments. So I have this one target. When the signal is crossing this target, then the signal would be higher. You can see the signal is higher. Okay, it says that it is crossing the target at distance. So this is the kind of the typical signal typical signal for the photoacoustic signal that is corresponding to this one. So that we this one, and then if we do the mapping, then we can get this kind of the images to be images. So for the reconstructions, it is not rigorous. The kind of the 1D signal, how you are writing in the computers, that you have to unwrap it. So whatever the signal, that you have to do it in the 2D matrix or the 3D matrix. And then of course, we need the certain kind of the filtering. It is quite associated with the noise that I come across. The kind of the transition, it is picking up kind of the noise from the environment, and then it is very sensitive to any kind of the breakage in the cable. That we have to take care of it. And this kind of the information, this is the time resolved. However, in our image that we would like to get it in the spatial resolve, the information with respect to the depth and the distance. that we have to convert this one. That we can achieve by use of the S equal to Dt, because the velocity that we can assume as the velocity of sound in the soft tissues. And this time is given from this one. From this one we can achieve the special result images. Yeah, this is some of the typical images that we did it. This is for the human ear. I think this may be my ear, and this is the image of the rat. So it gives the structures of the targets. That in other way, these are the mapping of the distributions of the optical absorption coefficients. This is what people start studying in the photoacoustic microscopy, photoacoustic imaging. Now, the question is that whether that is the conclusion of the story, that is the end of the story? No. Then, from the extraction of the photoacoustic signal, whether we can derive any other physical parameters of our interest. That is the question. Yeah.
I have a question. How long would it take to?
Basically, it depends on the scanning area. Yeah. I think I have a parameters. Speed. Oh, I think for this whole image, I think 5 micrometers per second I move it in one. Then for this one, I think 50 by 100. Then we have to multiply it. So it's order of the minutes. It's very interesting. So in this way, though the microscopy is very potential, then what about the real-time imaging? That is what people are looking for. But basically, I didn't include that part. No, people have achieved for the real time. Instead of the mechanical movement, so electronically people move it, scan it, so we can achieve the real time. That is what people has already established. That is also very interesting to use. And microscopy I can also discuss when I arrive to the results from the imaging system. So that we can achieve with the real time in the range of the microscopy areas. From the tomography. Application from the tomography reaching to the microscopy region. That is what I am talking about. The people who are working in the tomography regions, they know penetration depth is of the order of centimeters. They want to increase the resolutions touching to the microscopy. These microscopy regions, they know this resolution is very high, penetration is very depth. They want to increase the imaging depth. That is how people are moving. So now, what we are trying is that whether we can derive the flow velocity from the photoacoustic imaging system. That is what, so that the horizons of the applications of the photoacoustic imaging system can be improved. That is what we did is that if there is a flow, if it is detected by sensors, if there is a relative motions between the source and the detectors, then there is a frequency shift. However, the kind of the signal, considering this is a distributions of the sensors, these whole transistor surface that we can consider as a distributions of the elements. So the kind of this frequency shift over here to over here, it would be varied. It has a standard deviations. That is what we call as the bandwidth of the frequency shift. That is given by these equations. So this is the velocity of the particles, velocity of flow, and this is the operating frequency, and then this is the bandwidth broadening, and then this is the numerical apertures, and this is the Doppler angles. So from the experimental measurement of this BW, whether we can extract this B, that is our questions. What we propose is that we have one equations with the two unknowns. How we can get? Then, if we can achieve with the two equations by the linear algebra that we can resolve. For that one, what we did is that scanning system that will scan in the two directions that I will discuss in the next slide. For this one experimental approach that I will discuss it. So this is what I'm talking about. This we can interpret it is that is the variations of the frequency spectrum. If this is the case, from this theorem, it is given by this one. That is the correlations of the sequence of the signal nearby. So in our case, I think we did it for the 5 to 10 signal consecutive. Then we do this kind of operations, and then we got it this one. In the sense that from the experimental measurement of this left-hand side, then we can get it this one. Here we can estimate the side. How to get side? That is what our contributions. So this is the motion of the transistor. This is the flow. The kind of the signal that we get, photoacoustic signal, that is not only because of the motions. This is because of the, that is also contributed from the motion of the transistors. This is a resultant effect of the motions of the transistor as well as the flow. Then from the vector sum, then it comes to this one. So if this is the case, this is the cases for the motion in one direction. What about if we reverse this direction? This one, this one. So this is the two equations. So from these two equations that we know that this one, this is from the experimental measurement, this is from the experimental measurement, and these we know the motion of the transducer from the motion of the motion controlled by the stepper motor. From this one, that by solving these two equations, then we can get it the VF and the side ends. So this is the experimental results that we got it under the control system, where we use the microtube of the 500 micrometer diameters that is embedded in the tissue mimicking agar phantom, and then we characterize it. So it is quite matching to recover the this one. Then with this kind of the modality, we can achieve all the direction of flow and the magnitude of the flow. This is about the comparisons of the this one, our measured quantity against the true values. So with the 45 degree, it should be matching. So it is very close. So this is about the measurement in the magnitude that has a limited overviews. This modality is successful. Beyond this one, it is falling off. So other than this one, we also look for whether we can derive the elastic property of the samples from the measured photoacoustic signal. That is what we are looking for. The idea is that if we see the right hand side of the P naught, that is given by the beta by CV and B square, and the absorption coefficient and this one. So here is in the right hand side, here is a Hermann coefficient of expansions, that is the characteristics of the elastic properties of the medium. If there is a changing, then we can get a mechanical property from this one. This is about the characterizations. For this one, we have a target where there is no contrast with adoption and all these things where there is no. And then when there is a variations in the elastic property of the samples that we got it, that we embedded in the systems over here. Different target with a different in the contrast in the elastic coefficients, then that is reflected over here. In the sense that photoacoustic signal can give the signal contrast with respect to the elastic property of the samples, so that one can derive the elastic properties of the samples from the photoacoustic imaging system. However, this is the qualitative, not the quantitative. About quantitative, that is what people are now focusing on, how to get the quantitative values of the elastic properties. So it is quite independent of the size of the target that we found it. We change with this one, and it is independent of the size of the targets. Yes, one more. The kind of the frequency response that we are going to use for detecting the kind of the physical parameter is quite different. That I would like to share it to you. For optical absorptions, the frequency of the lower frequency range of the 1 to 10 or 15 megahertz is more suitable. But that cannot be used for the detection of the elastic property. So that we got it by the 50 megahertz. This is also very nice to share it to you. When we first tried with the conventional ultrasound transmission that is people use for the photoacoustic of the 1 to 10 megahertz, then we don't get any signal, then we tried with the 50 megahertz that we got it. One to remark is that the kind of the signal is framed from the elastic property and absorption. This is very, very low as compared with the contrast in the optical absorptions. That has to be. And another challenging thing that is happening in the photoacoustic imaging that people are trying to is that how to discriminate the contributions of the physical parameter to the detected signal. It is contributed from the absorption coefficient, elastic coefficients, temperatures. Then, for an unknown sample from the detected signal, how to segregate the contribution from the different signals. That is also what one of the area of the research people are looking for. Yeah. So for this one, I stop over here.